For this video, we're looking at something called the chain rule to take derivatives. Imagine that you had a function y equals x plus 2 squared. And all you knew was the power rule. So you know how to multiply down, subtract 1, but you've got these parentheses you need to get out of the way. So it's not that hard. You would just square it. Y equals x squared plus 4x plus 4. You can use FOIL, box method, whatever you like. So if I wanted y prime, it's pretty easy. I use the power rule and it's 2x plus 4. Well, that's great. And then along comes a problem like this one. What if y equaled 3x plus 2 to the 6th? That's not nearly as much fun because you'd have to multiply 3x plus 2 times itself 6 times. So we just say no, find another way. And that's what people did. So in math, we often use something called substitution. If something's making a problem hard, you take it out, substitute in something else, work the problem, and then at the very end, swap it in. So I'm going to look at this function in a different way. The thing that's making this function hard is not the 2, the squared out here. That's not what's making it hard. If it was just x squared, I know how to take the derivative. It's the fact that this isn't just an x, it's an x plus 2 that's being squared. So I'm going to substitute something in for the x plus 2. And you can declare any variable you like to do this. I'm going to use a u. So u equals x plus 2. And that turns my function into a u squared. So now I just have one variable to a power, and I can use the power rule, I think. So I'm going to multiply down, subtract 1, and that is a 2u to the first. Here's the problem. Your goal is that you want a dy dx, the derivative of this y with respect to x. I want a dy dx. That's what this y prime is, dy dx. If I just say it's 2u to the first, that's actually the derivative of y with respect to my u. It doesn't match. What I really would like to do is figure out how I can go from my dy du into a du dx. And if you think about it, I want my dy to stay, I want my du to go away, and I need a dx. So it's like we're multiplying by a du dx. If you think about it like multiplication, you think, oh yeah, the du's cancel. And that's how this works. It's not quite what you're really doing, but algebraically it makes sense. So that's what we're going to do here. We're going to identify a u, but then my next step is to actually find a u prime. So I can write it as u prime, or I can write it as du dx. And in this case, the derivative of my u is just a 1. So once I have that, I know that I can take the derivative of my y with respect to u, multiply it by my du dx, and I'm actually going to get my dy dx. So it looks like that it would be 2u to the first times u prime, and that's really hard to see the difference. So this one is my dy du, this is my du dx. Multiplied together, I get my dy dx. So this one would be 2 times my x plus 2 times 1, 2u times my u prime. And this is my dy dx, which you can see is the same thing as 2x to the 4th. So working from start to finish here, the first thing I'm going to do is identify what is my u. And it's usually found inside the parentheses. So I'm going to say u equals 3x plus 2. I'm going to right away figure out what my du dx is, my u prime. And that is a 3. Then I'm going to rewrite my function with respect to u instead of x's. So I'm going to say this is really like a y equals u to the 6th. I'm going to take the derivative of my u to the 6th, so that is 6u to the 5th, and I'm going to multiply it by my u prime. U prime. So this right here is my dy du, the derivative of y with respect to u, and I'm going to multiply it by my du dx. That's going to give me the dy dx. I substitute back in. I have y prime equals a 6 times u, which was 3x plus 2, to the 5th times my u prime, which is a 3. So my final answer, cleaning it up, would be y prime equals 18, 3x plus 2 to the 5th. So I'm going to work several more problems, but I want you to see what you're really doing is you have an inside function, 3x plus 2 to the 6th. So my inside function is 3x plus 2. The outside function, you can think of it as something to the 6th. I'm going to take the derivative of the outside, so it becomes my 6u to the 5th times the derivative of the inside, 3. 6u to the 5th times u prime. 6u to the 5th times 3. And that gives you your derivative with the chain rule. So for my next example, I'm going to do something a little different. I'm going to add a square root. So imagine I have y equals the square root of, let's say, 5x squared plus 6. I'm going to choose my u to be everything inside of the square root. You can imagine that there's a set of parentheses here surrounding it, and I usually try to make u what's inside of my parentheses. So u equals 5x squared plus 6. That makes my du dx, or my u prime, equal to 10x. Now I rewrite my function in terms of u. The u is inside a square root, so I could say it's the square root of u, which I know is equal to u to the 1/2 power. I'm going to take the derivative of this to get my dy du, so it's 1/2 u to the negative 1/2. This is dy du. I'm going to multiply it by u prime, which is du dx. I substitute back and I will have my y prime. So y prime, my dy dx, equals 1/2, put my u in, 5x squared plus 6 to the negative 1/2 times my u prime, which is a 10x. So looking at this again, it's the derivative of the outside function, u to the 1/2. It's 1/2 u to the negative 1/2 times the derivative of the inside function. And it's important to note you leave the inside function alone when you're doing the derivative of the outside. I'm going to take one more step and rewrite this. Y prime equals, and if I look at this, 1/2 of 10x is a 5x. This will be the square root in the denominator of my 5x squared plus 6, and that is finished. Another example might be, let's say you had y equals 3 divided by, and let's just make it 2x squared minus 6x to the 3rd, the parenthesis there. So for this, u equals 2x squared minus 6x, so my u prime will equal 4x minus 6. If I rewrite my function, it's 3 over u cubed, which is equal to a 3u to the negative 3. I do the derivative of the outside, negative 9u to the negative 4th, leaving my inside alone, times the derivative of the inside, my u prime, and I will have my y prime. So my y prime will equal negative 9. My u is 2x squared minus 6x, now to the negative 4th, times 4x minus 6. If I rewrite this to make it look a lot prettier, I have a negative 9 in my numerator, a 4x minus 6 in my numerator, and I have 2x squared minus 6x to the 4th in my denominator. And there might be some things I could cancel out, but I'm really not going to right now. Okay, I'm going to do one more problem because I want to do a little bit of trig. So let's say we have y equals cosine of 4x to the 5th plus 6x. So my u would equal 4x to the 5th plus 6x. My u prime will equal 20x to the 4th plus 6. If I rewrite my function with u, it's cosine of u. Now I'm going to take the derivative of my outside function, so outside function is cosine, so that'll be a negative sign. Leave my inside function alone of u, times the derivative of my inside, which is u prime. I rewrite it. So y prime equals a negative sine of my 4x to the fifth plus 6x times 20x to the fourth plus 6. You could call that done. Generally, we would take this, move it to the front of the sign to make it look a little bit better, but that is the process. The multiplying by the u prime is like connecting the chain. So it's called the chain rule, but you can call it u substitution. A lot of people think of u substitution only for integrals, but you're really substituting in, substituting out, and it really doesn't matter what letter you use. As long as you know it's the derivative of the outside function, so derivative of the outside, leave your inside alone, times the derivative of your inside function, you'll be fine with the chain rule.